Hello, my name is Zachary Ivie. Thank you for watching our final presentation for Deep Learning course at University of Tennessee, Knoxville. Our group consists of Matthew Robinson, Tate Taczak, Luke Whatley, and myself. AI has many use cases, but one in the field of medicine is image classification. For our project, we focus on brain tumor detection. We trained an AI model to classify images into two categories: images depicting brain tumors and images that don't. To train an AI to do this, we have to feed it real images of MRI scans showing both tumorous and healthy brains until it can learn to tell the difference. Our approach to increase the accuracy of this distinction is fairly straightforward. We want to feed the model more images. Working with MRI images present a lot of challenges though. Actually interpreting the images requires medical knowledge, which is expensive and scarce. Taking MRI scans is time consuming, the machines are expensive and not easily accessible. MRI images are sensitive because images of people's faces can be reconstructed unless identifying features are removed. Due to the cost and scarcity of real MRI images, we want to generate new images for training from the real ones we have available. Traditionally, this is done by making transformations to the image, such as cropping, translating, and rotating real images to make additional images for training. To tackle this problem, we took a slightly different approach. In our method, we used a generative adversarial network to generate additional images for training. We then compared the GAN-augmented dataset to the unaugmented baseline and a dataset augmented using transformed images. The baseline dataset came from the Kaggle dataset, which contains 1,300 MRI images collected from MRI scans. The type of tumor is labeled by professionals if a tumor is present in the image. Here we have the model diagram for our classification model. We opted to use a convolutional neural network for image classification. Images go through 4 convolutional layers consisting of convolution, max pool, and batch normalization. Then average pooling, 3 fully connected layers with batch normalization, a dropout layer for regularization, one final fully connected layer that goes to 2 neurons, tumor or no tumor. Softmax is used for the final output. And here we have the model diagram for our image generator. We used a generative adversarial network, which contains a generator and a discriminator. In a GAN, the generator is trained to create fake images that are similar to the real input images, while the discriminator is trained to distinguish generations from real inputs. This competition between generator and discriminator causes image generation to be harder and harder to detect as fake, resulting in more authentic generations. We assembled 3 training datasets for our models to use. For our datasets, we use 1,000 real images and synthesized 100 fake images for augmentation. Our testing dataset contains 150 images with tumors and 150 without. The baseline model was only trained on 1,000 real MRI images from the Kaggle dataset, while the GAN augmented model also had 100 GAN-generated fake images. The transform augmented model had 100 transformed images instead. Here we have the training and testing accuracy and loss graphs for each model. All 3 models had roughly similar accuracy and loss, with the augmented datasets performing slightly better. Breaking out each model's performance into a confusion matrix, we see that the baseline model had the lowest accuracy with only 90.67%. The GAN augmented dataset had the highest overall accuracy with 95%, with the transform augmented model trailing closely behind with 94.67%. In conclusion, adding either GAN-generated images or transformed images to the original dataset improved the accuracy of classification. For our specific problem of cancer detection, the dataset with transformed images was arguably more useful because the resulting model had less false negatives than the GAN-augmented model. Some ideas for improvement that might have been fruitful to explore in the future include possibly using variational autoencoders or vision-enabled transformers for image generation instead. This concludes our presentation. Thank you for watching.